All right, so I want to go over a few quick results without proofs, but a few important results about big O estimates or big O comparisons of functions. So the first one is that n is big O of 2 to the power n. So n is big O of exponential 2 to the n. Now, and that is going to be something that you can prove with a strategy called induction, which is going to be introduced later this semester in Chapter 5. So we're going to hold off on proving that, okay? Can be proved with induction. And the thing that you're going to prove with induction is that n is less than 2 to the power n for all positive integers n greater than or equal to 1. Okay? So that's going to establish that. So now, what that means, if n is less than 2 to the power n, you can take this inequality and you can do the log of both sides. Log base 2 of n is less than log base 2 of 2 to the n. And from that, obtain the following, that log base 2 of n is less than n. Is going to be, actually, I'll write it this way, is big O of n. Okay, and that's because that over here, we've got log base 2 of n is less than n. So log n is going to be big O of n, okay? So, and then the third one, again, I'm going to present without proof, is that, and I'm switching colors just because I don't like that pen, sorry. So we're going to prove that n to the power k is going to be big O of 2 to the n, in fact, for any natural number k. So what that means is that power functions, n to the k, any power function, and therefore any polynomial, because you can kind of prove that, power functions and polynomials are of the same order, kind of what I discussed last video. Those are always big O of 2 to the n. This essentially means that exponential growth is faster than any polynomial growth. No matter how fast polynomial growth is, even if you take n to the power 2,000, that's still going to be a slower growth rate than even the slowest of all exponential functions. Something as simple as 2 to the n. So all exponential functions grow faster than all polynomial functions. So there we go. So let's see. A couple other theorems. One has to do with what happens if you take two functions and add them together. Let's see. If f1 is big O of g1, and f2 is big O of g2. Okay, so if you have two functions, f1 and f2, and you have some big O estimates for them, big O boundaries, or you often call these big O estimates because they're sort of like upper bounds on the rate. So if f1 and f2 are big O of g1 and g2 respectively, then if you add these together, f1 plus f2, that's going to be big O of something. And the thing that it's the big O of is going to be the maximum of g1 or g2, where g1 and g2 are whichever one of those grows faster. That's going to be what this is a big O of, okay? So as an example of that, say you take the function hang on a second. Say you take the function, just a moment. Yeah, 1 plus log of x. That's going to be big O of the bigger of the two of these. So one is big O of 1 log x, big O of, let's say this is like 4 actually. Just so 4 is big O of 1. Log x is going to be big O of log x. And so this is going to be big O of log of x, like that. So that's like you take the bigger of the two, right? But then say you do something more like x, maybe like 2x plus 5 plus log of x, okay? Well, log x grows slower. Let me pull back my graph here that we started with, right? Log x grows faster than the 1, right? So it's going to grow faster than a constant function, but log x is going to grow slower than a linear function, 2x, right? So you basically take the maximum of all of those, right? 2x is big O of x, so this is going to be big O of x as well, okay? So just taking a linear function, linear functions are all big O of x, but a linear function plus a log function, which is slower, is also still going to be big O of x, all right? It doesn't change its growth by adding a slower function. This is basically why, you know, you can take, like in the previous example, and, you know, you can take x cubed, like a multiple of x cubed, which is big O of x cubed, and you can add these slower functions on the end, right? You can add lower degree polynomials on the end here, squared, first power, and constant, right? And that doesn't change the fact that it is big O of x cubed, all right? Because these are slower. If you, one more example, if you take like 10 to the power x plus 5x to the power 200, right? The 5x to the power 200, that might be a really high power of x, but it's still slower than 10 to the x, right? So this is still going to be big O of 10 to the x, like that, right? So there's a theorem about adding functions together, and there is a theorem about multiplying functions together, which we're not going to use as much, but I will introduce it. If f1 is big O of g1, and f2 is big O of g2 again, then f1, f2 is going to be guaranteed to be big O of g1 times g2. So this one is and you don't have to do a maximum for this one. For this one, you just take the product, right? You just, if f1 is big O of g1 and f2 is big O of g2, you just take g1 times g2, and that'll give you a big O estimate for f1 times f2. All right, so yeah, so that's that. I think that is going to pretty much sum up this video. Okay, these are just a few results that are kind of useful. In the next video, we're going to make a couple of new definitions.